Alright, so let's continue on the limits and their property. This section we're going to learn how to find limits graphically and numerically. And the objectives will be estimate a limit using a numerical or graphical approach. Learn different ways that a limit could fail to exist, and study and use a formal definition of limit. So the introduction to limit. Limit is a trend for the graph of function at the particular x equals c. Right? Suppose we are asked to sketch the graph of function f given by f of x equals to x cubed minus 1 over x minus 1. In this case, x cannot be equal to 1. That's part of the domain. So the domain is all real numbers except 1. And for all values other than x equals to 1, you can use standard curve sketching techniques to graph this. However, at x equals 1, it's not clear what to expect. So let's take a look at that and then try to get something out of it. So to get an idea of the behavior of the graph of f of x near x equals to 1, you can use two sets of x values. One of them is from the left, right? The values on the left could be 0.999, could be 0.99, 0.9, 0.75. As you can see, the number should be listed in increasing orders. So 0.75 is the smallest numbers among all these numbers selected. 0.9, 0.99, 0.99, and 1. And we try to figure out what happened at the 1. That's a goal. And also we're going to pick some values on the right hand side of 1, 1.01, 1.01, 1.1, 1.25. As you can see, again, it's in the increasing order, right? So in order to find out what the limit behavior at this particular point x equals 1, so let's see what a y value is. So for x equals to 0.75, and f of x is going to be equal to x cubed, so 0.75 cubed minus 1 over 0.75 minus 1. And if you perform the operation, it turned out to be approximately 2.313. That's how we get all these y values, by replacing x value with the corresponding x values we selected. As you can see, the numbers on the front left hand side of x equals 1, the number getting closer to 3. From right hand side, as you can see, number also from right hand side go from this direction. As you can see, number also approaches 3. So safely speaking, we can say that at x equals 1, the limit will approach 3, right? When x approaches 1, limit of f of x approaches 3. And that's what we see from this numerical table. And this is a very good way of investigate limit at any particular x values. This method has been used a lot, right? And as you can see, this is a graph of the function. It actually is a parabola, sort of a parabola, except at x equals 1. At this point, that's an undefined point, so that's why we put a hole there to indicate that at that particular point, the graph is discontinuous, right? So the graph of f is parabola, but that has a gap at a point 1,3, right? As shown in the figure 1.5. Although x cannot equal to 1, you can move arbitrarily close to 1. As a result, f of x move arbitrarily close to 3. So basically, using limit notation, you can write limit when x approaches 1 for f of x equal to 3. This reads as the limit of f of x as x approaches 1 is 3. So this is an interpretation of limit. So now let's talk about the informal definition of the limit. If f of x becomes arbitrarily close to a single number L, as x approaches C from either side, meaning from both sides of the number, both sides, from left hand side and right hand side, right? Left and right. The limit of f of x as x approaches C is L. This limit is written as limit when x approaches C for function f of x equals to L. L is a constant. Okay. So this is the informal definition of a limit. And we're going to see this a lot. So let's take a look at evaluate function f of x when for x over parentheses square root of x plus 1 minus 1 at several points near x equals 0, and then use the result to estimate the limit. If you do the direct substitution, right, meaning if you just plug in x equals 0 into this function of 0, so you're going to have 0 over radical of 0 plus 1 minus 1. So 0 over 1 minus 1. So this is radical 1 equals to 1. 1 minus 1 is also 0. So we have a 0 over 0. This is what we call indeterminate form. Determinant. Meaning nobody knows what that is. So I'll just give you a intuition what happened here. So we want to figure out, we want to investigate when x approaches 0 for this particular function f of x, what happened to the limit. Okay, so we create a table just like what we did in the previous example. So pick some value from left hand side of 0. So starting with negative 0.01, and second one is negative 0.001. The third one is negative 0.0001, and 0. That's what we are looking for answer. And we pick 0.0001, 0.001, and 0.01. So all these numbers are in the increasing orders. As you can see, in order to find these values, you just get for x equals to, let's say, negative 0.01, you just get to plug into the f of x. F of x is going to be equal to x, which is negative 0.01, over square root of negative 0.01 plus 1 minus 1. And the result of this becomes 1.99499. And that's how you find out the y values. That's why we have these y values. All these values could be calculated in the same way. So now let's take a look at the left hand behavior, right? Well, as you can see, the number getting close to 2. And on the right hand side, similarly, the number getting closer and closer to 2. So we should be confident that at x equals 0, when x approaches 0 from left and right hand side, limit when x approaches 0 for f of x, in this case our function is x over square root of x plus 1 minus 1 will be 2. Right? From the table we can come up with this conclusion. From the result shown in the table, you can estimate that limit to be 2. Okay, so this limit is reinforced by the graph of f of x. So f is undefined at x equals 0. That's why I put a circle there, right? And at this particular point, this number is 2. On the left hand side, this is getting closer and then closer to 2. Right. On the right hand side, the number is getting closer and closer to 2 as well. That's why 2 is the limit when limit of f of x as x approaches 0. So let's take a look at some cases for the limits that fail to exist, meaning no limit. Let's take a look at several examples. There are 3 different cases where a limit does not exist. So the behavior that differs from the right from the left show that a limit when x approaches 0 does not exist. So on the left hand side, as you can see, when on the left hand side of the 0, now our function f of x is going to be equal to x of x. Since on the left hand side of 0, so x is negative, so get rid of that, you get x. Divided, you get negative 1. Okay. On the right hand side of the 0, then f of x on the right hand side, x value is positive, so get rid of the absolute value. You get x over x is 1. As you can see, these two numbers are not equal to each other. So algebraically speaking, limit does not exist. But let's take a look at the detailed solutions. Why this limit does not exist. Okay, this is something, this is a summary of what we just did. So as you can see, when x is greater than 0, then we have a meaning on the right hand side. From right hand side, this is the left side. When x less than 0, then we get negative 1 here. So these two numbers are not equal to each other. And graphically speaking, when x approaches 0 from right hand side, you get limit is 1. This is from left hand side, and then this is from right hand side. From left hand side, the y value approaches -1. This is -1 right here. And these two numbers does not converge, meaning they're not the same. So limit for f of x when x approaches 0 does not exist for this particular function. So this means that no matter how close x gets to 0, there will be both positive and negative x values that yield f of x equals 1, f of x equals -1. So that means limit does not exist, right? So specifically, this is what they call delta. It's Greek letter delta. Delta is a positive number. And for x values satisfying an inequality, for absolute value of x is greater than 0, less than delta, you can classify the value of absolute value of x over x as follows. Negative delta is common 0. So negative x value yields -1, and positive x value yields +1. Because absolute value of x over x approaches a different number from the right hand side of 0, then it approaches from the left hand side. Then the limit when x approaches 0 for f of x does not exist. Does not exist. So this is one particular case that the limit fails to exist. So there are three different common type of behaviors associated with non-existence of limit. First one is f of x approaches a different number. Just the previous example exactly matches with this one. From the right hand side of c, then it approaches from the left hand side. So meaning left hand behavior is different from right hand behavior. Second one, f of x increases or decreases without boundaries as x approaches c, and it becomes infinity, right? Approaches infinity, plus minus infinity from left and right. F of x oscillates between two fixed values as x approaches c. So that's the third case when the limit that failed to exist. So let's take a look at the formal definition of limit. Let's take another look at the formal definition of limit. Informal definition of limit. If f of x becomes arbitrarily close to a single value L as x approaches c from either side, then the limit of f of x as x approaches c is L. Right? That's an informal definition. If you look at it, this definition looks fairly technical. Even so, it is informal because the exact meaning has not yet been given to the two phrases. If f of x becomes arbitrarily close to L when x approaches c. So the first person to assign mathematically rigorous meaning to these two phrases was Augustin Louis Cauchy. He's a mathematician. He's epsilon. This letter is epsilon. And delta, as we mentioned earlier, definition of limit is the standard used today. So let's take a look at this graph. So this is delta. So x equals c, that's what we are looking at. So within a very tiny little intervals here, because delta is very small positive numbers, you can view the sigma as something like infinite many zeros here, all the zeros in between. Okay, that indicates a very tiny little number. That's what this delta is about. And here, as you can see, since the x value is in the interval, the y value is also in the interval, but it's also very tiny little intervals here. Right? So then when x approaches c from left hand side and right hand side of x equals c, then f of x becomes arbitrarily close to L, right? Means that f of x lies in the interval L minus epsilon, comma L plus epsilon. Again, epsilon is very small positive number. Okay. Both delta and epsilon are very small positive numbers. So this is the formal definition of limit. And use absolute value, you can write this as f of x minus L. Absolute value of f of x minus L is less than epsilon. The phrase x approaches c means that there exists a positive number delta such that x lies in either the interval c minus delta comma c or in the interval c comma c plus delta. And the fact that could be concisely expressed by the double inequality, meaning absolute value of x minus c is greater than 0, less than delta. Then f of x minus L is going to be greater than 0, less than epsilon. It goes hand in hand. Meaning x approaches c, this is c, that's c minus delta, c plus delta. That's for the x value. For the y value, this is L. It's L minus epsilon. And the right hand side is L plus epsilon. Okay. So this is a formal definition of limit. And that's just summary what we just did, right? First inequality is this. Absolute value of x minus c is greater than 0. Second inequality is absolute value of x minus c is less than delta. So x within a distance of delta of c. So let's take a look at formal definition of the limit. There have to be a function defined on an open interval containing c, except possibly at c. That L be a real number. The statement limit when x approaches c, f of x equals L, meaning that for each epsilon is greater than 0, there exists a delta is greater than 0, such that if absolute value of x minus c is greater than 0, less than delta, then f of x, absolute value of f of x minus L is less than epsilon. So given the limit, let's take a look at example, find the delta for given epsilon. Given a limit, when limit for x approaches 3 for function 2x minus 5 equals 1, this is given, right? Find delta such that 2x minus 5 minus 1, absolute value of that is less than 0.01. Whenever absolute value of x minus 3 is greater than 0, that's the epsilon. So here you can easily just expand it, 2x minus 5. Minus 5 minus 1, less than 0.01. So here is 2x minus 6, less than 0.01. If you factor out 2, put it in front, x minus 3, less than 0.01. So now divide both sides of the equation by 2. The absolute value of x minus 3 is less than 0.01 divided by 2. So as you can see, 0.005. So this absolute value definitely is greater than 0, less than 0.05. And this is actually the delta we're looking at, right? So delta equals 0.005. So this is algebraic way of finding the answer. So this is, as you can see, this is typically just becomes f of x minus L, right? Less than 0.01. Now we go back to x minus c. This is x minus c. Eventually we end up with that. This is actually x minus c greater than 0, less than epsilon. That's why we're going from this to this. So this is our epsilon, and that's our delta. Okay, this is exactly f of x. This is L, right? As we can see here, limit, that's L. Okay, so basically we're going backwards and finding the epsilon and delta. So graphically speaking, as you can see, this is the graph for this. So at this particular point, when in this case epsilon is 0.01 and the delta is 0.005. So for this tiny little interval yields that tiny little interval for limit. So that's why the epsilon is 0.01 and delta is half of that, 0.005.